Second part of the text summarization lecture. Last time we built up the intuition for text summarization. We also went through different metrics, different approaches in terms of extractive summarization, in terms of abstractive summarization. We also covered a couple of models which mostly used extractive summarization. And today we're gonna actually take that to the next step and cover more approaches which are in the abstractive summarization domain. We're going to start today by the encoder-decoder architectures and the RNNs. We're going to go from this into the pointer generator networks and check how do the pointer generator networks actually overcome the shortcomings of RNNs. We're going to go through BART and PEGASUS too, being a couple of the standards algorithms in the abstractive text summarization field. Then we're going to finalize by T5 and ProphetNet. We're going to also keep a rolling table of the evaluation metrics in terms of Rouge 1, in terms of Rouge L, and compare different metrics on how they act, different models on how they perform on the CNN Daily Mail dataset with respect to the Rouge metric. So let's dive into it. In text summarization, the original long piece of text is input to the decoder. Each word in the text is typically represented as a word embedding or a vector, which is then processed by the encoder. And the final state of the encoder would be a representation that encapsulates the meaning of the entire original text to actually have an understanding of what is this text about. Like if you also go back to the human process of generating summarization, you need to understand in the beginning. And that's the game for the encoder. Then going to the decoder, this decoder takes this final state and then generates the summary, usually I have to say, one word at a time. It also, in that domain, typically uses attention mechanisms, which you also have been going through on the previous lectures, to focus on different parts of the input text. At each step of the output generation. What does this allow for? This allows the model to generate an output that is not just dependent on the last state of the encoder, but also takes into account specific parts of the input text. Talking generically about encoder-decoder architecture, let's go more specific. Let's put RNNs inside. Let's assume the architecture in front of you, where we have here an encoder, which is a single layer bidirectional LSTM for understanding the input text, and the decoder with a single layer unidirectional LSTM. I hope you also by now imagine why they actually put the bidirectional LSTM in the understanding part and the unidirectional in the generating part. It also should make sense right now. Then here, the decoder receives the word embeddings. The tokens of the articles here are fed one by one into the encoder, producing a sequence of encoder hidden state, the HI. And then decoder receives the word embedding of the previous word. This actually, while training, would be the previous word of the reference summary that we have. And at test time will actually be the previous word emitted by the decoder. Then here we have the attention distribution. How can we view this, or how can we model this? This actually can be viewed as the probability distribution over the source words that tells the decoder where to look to produce the next word. Next, The attention distribution is used to produce a weighted sum of the encoded hidden state, which is viewed as the context vector. Let's look at this one level deep. So we said on each step T, the decoder or the our single layer unidirectional LSTM receives an embedding of the previous word and a decoder state ST. And then we calculate the attention distribution as per the normal attention equation. And then we get the softmax, whereas in that perspectives, you probably also know from previously that V, WH, WS, B attention are actually learnable parameters. And then the attention distribution is used to produce here our context vector. And then the context vector is concatenated with our decoder state to produce our vocabulary distribution. And our final distribution to predict the word would be actually this concatenation softmaxed in order to turn it into a probability distribution, which is actually noted here. Coming from this, what are the shortcomings of RNNs, or what are the issue of RNNs in the abstractive summarization domain? Well, they tend to repeat themselves. This is one point that they actually do, because they normally do not keep a long memory of what has been previously generated. So they are more liable to repeat themselves in that perspective. And the first and third points are very much related in that perspective, that they are also liable to reproduce factual details inaccurately. Why is that? Simply because the model has to have seen a certain vocabulary distribution during the pre-training or the training perspective. And then it will only generate words which it has seen before. It has to see those words to be able to generate them. So if there are some out of vocabulary words or factual details that were missing in the training data, they are not going to be there in the output. So in that perspective, they are very restricted to their preset vocabulary. Let's take a look at how this architecture performed in terms of Rouge 1, Rouge 2, Rouge L, the sequence to sequence plus attention on a 50K vocab training produced a Rouge 1 of 31.33, Rouge 2 of 11.81, and a Rouge L of 28.83. Let's now build the intuition towards the pointer-generated networks. The pointer-generated networks for text summarization is actually, as the name implies, right, is pointer networks and generator networks. The pointer networks is a component of the model that allows it to copy the words directly from the input. And the generator network generates words from a fixed size vocabulary, such as the ones that the previous unidirectional LSTM was doing on the decoder aspect. And then the model can dynamically choose between either it should copy the word from a source text while dealing with out of vocabulary words or important words or rare words, and the other side of generating a word from its learned vocabulary, where it can generate probably more fluent, more grammatical text, and so on and so forth. This is an example which was provided in the paper with original text and the comparing the baseline sequence to sequence plus attention to the pointer generator networks to the pointer generator networks plus coverage. So you see here, for instance, taking this factual information, this Muhammadu Buhari is not generated in the baseline sequence to sequence, but it's there in the pointer generator networks because the model decided to copy this from the original text instead of generating a word at that perspective. So The idea of pointing or copying mechanism in the context of pointer-generated networks, as we mentioned, is to selectively copy words from the source text directly into the input instead of always generating words from a fixed vocab. This is important in many tasks, one of which is actually the abstractive summarization, because there might be, as we said, some words which are out of vocab or rare words, or the model hasn't seen those words often during training, and the pointing mechanism allows the model to actually handle such cases effectively. Now let's actually take a look on how this works. First block we take a look at is the attention distribution. So the pointing mechanism relies on the attention distribution over the source text. The attention mechanism in general allows the model to focus on different parts, right? On different parts of the source text while generating each word in the output. It computes an attention score for each word in the source text, indicating how relevant that word is for generating the next word in the output. And these scores are then normalized using a softmax function to create our attention distribution. Let's denote this as A here. Then the second part we will talk about is the pointing distribution. So the attention distribution A is then used to create a pointing distribution, which is a probability distribution over the source text, where actually the probability of each word being selected or pointed to is equal to its attention weight. So, for instance here, if the words Argentina has a high attention word in the current context, it will have a high probability in the pointing distribution, meaning that the model is likely to copy Argentina from the source into the output. Now that leaves us with the third part of how would the model decide whether to actually copy or to generate. And this happens with this little guy out here, this pgen. The pgen belonging to 0 or 1 is generated at each and every decoder time step. If the pgen is high, then the model is more likely to generate a word, because in that perspective it has more weight out here. It weights it more. It gives it more importance. And then, of course, on the other side is on the 1 minus. It gives the advantage towards the source text. And then, in that perspective, the model, with this interpolation of the pointing distribution and the generating distribution, is able to dynamically choose between copying the word and generating the word. Now, let's actually talk about the next thing. So, we said that RNNs are usually repeating themselves. But how do pointer-generated networks leverage that? This is done by the coverage mechanism. The coverage mechanism is actually used to keep track what has been summarized in the past, which discourages the repetition for the model. This coverage vector, CT, is maintained as the sum of the attention distributions over all previous decoder time step. And this coverage vector is used as an extra input to the attention mechanism, changing our attention mechanism from that to having an additional term out here. And then an additional coverage loss is also added to the loss function. CT is an unnormalized distribution over the source documents, words, that represent the degree of coverage those words have received from the attention mechanism so far. And since they are actually unnormalized, this is the reason why we actually put the hyperbolic tan out here too, or like is also is unnormalized, so that the hyperbolic tan can also take it into consideration and bound it back to a bounded range again. And then adding it to the coverage loss makes the model more or less penalizes the words that have been already covered within the attention mechanism. And in that perspective, it avoids or decreases the repetition that was actually introduced, or like that you would see more in an RNN, and allows for more and more new words, perspectives, ideas, and so on to come over there. So the pointer generator networks out here, we talked about the pointing versus copying. We talked about the interpolation. We talked about how this PGen is used towards the interpolation, which is a key point of the pointer generator networks. We also talked about a coverage mechanism, which is a mechanism added to the pointer generator networks to minimize the repetition with respect to the summarization. Taking a look right now, the pointer generator networks score more than the sequence to sequence plus attention models, and adding the coverage is actually useful. So the root score went up from using the normal pointer generator networks to the ones that are having the coverage on. Now let's actually talk about BART and PEGASUS. Well, the guys for BART were really smart. So they said, okay, what is there are two main approaches that are done currently. Some people are doing BERT, some people are doing GPT. But how do we get the best of both in order to make our summarization approach very efficient? And that was the introducing BART into the topic. They said, okay, if we remember how BERT was actually bidirectional and having an autoencoder nature. This is well suited for downstream tasks, as for instance classification. Why? Because it gets more or less the whole perspective or the most understanding of the input text. And then GPT is very well suited for text generation, being a unidirectional and being autoregressive. If you remember a couple of slides back, this is very close to what we did with the bidirectional RNN or LSTM in the encoder and a unidirectional LSTM in the decoder. So they said, actually, why not sticking BERT and GPT together, using BERT for understanding, GPT for generation, depending on the autoencoder nature and the autoregressive nature. And then they took a standard transformer-based architecture of Encoder-Decoder that generalizes BERT and GPT towards text summarization. BART, they actually trained via a noise function to corrupt the text, and the model learns to reconstruct the input text, and is fine-tuned as a standard sequence-to-sequence model from input to output. So, as we said out here, is a transformer encoder and a transformer decoder having BERT and GPT stuck together and being used for understanding and generation. So for each and every text sequence in input, BERT encoder outputs an embedding vector for each token in the sequence, as well as our additional vector containing the sentence level information, which, like, from BERT, we have the CLS token, we have the SEP token. And in this way, the decoder can learn for multiple tokens and sentence level tasks, making it actually robust starting point for the future fine-tuning tasks. So if we take a look at how this noising mechanism works, or how they did the text corruption, more or less, they tried multiple approaches. First of all, they tried token masking. So random tokens are sampled and replaced with the mask element, like masked language modeling, very normal stuff. And then they said, like, okay, let's try token deletions. So random tokens are deleted from the input, and the model at that point would decide which positions have those missing inputs. So it adds one more level of complexity towards the pre-training task, making the model also more aware to where to place the missing inputs. Then the text infilling, inspired by the span BERT, actually teaches the model to predict how many tokens are missing from a span. So in that perspective, it actually would here have to know that B and C are missing in that perspective, right? And in that, it also knows how, or is more pre-trained rather than the normal masked language modelings. It knows how much tokens to generate and how many words to put in, and so on and so forth. Then sentence permutation. The document is divided into sentences based on the full stop, and the sentences are shuffled in a random order. And that also makes the model more aware of the ordering with respect to the sentences, because it has to know that this sentence comes before that one, and that one, and that one. And then the document rotation, it actually, a token is uniformly chosen, and the document is rotated so that it begins with that token. So if you have like, I have a pen as an example, it becomes like pen, I have a. And the model should actually also organize and make like outputs that I have a pen is the right sentence. With this, actually, they made sure that the model knows more, or like is pre-trained on something that is more than masked language the normal masked language modeling. And actually, in the end, the authors said that using only text infilling and sentence permutation transformation, with about 30% of the tokens being masked and all sentences permuted, this brought the best performance for BART. Then going from BART to PEGASUS, we're still actually going through a transformer encoder, transformer decoder architecture. PEGASUS is actually short for pre-training with extractive gap sentences for abstractive summarizations. Here, I actually would like you to note two different things. First is the pre-training aspect. Second, extracted gap sentences. Because what they do actually here is that they said, okay, on BART, we had a pre-training objective, which is still for a normal language modeling. It doesn't have to say something, or it doesn't have to be specific to text summarization. They said, okay, let's do a pre-training objective, which is more tailored for abstractive summarization tasks. And then their hypothesis was that fine-tuning performance would actually improve by choosing the pre-training self-supervised objective, which is close to the downstream task. So they utilized the pre-trained transformer encoder-decoder architecture. And for that perspective, they used actually gap sentence generation. Sentence generation is actually mimicking an idea of a pseudo summary. So in that perspective, if we see out here, it removes or the training input is the document with those missing sentences. And the training output would be those missing sentences concatenated together. So in that perspective, the model is, instead of masked language modeling pre-training, is actually pre-trained on getting a pseudo summary, which is presented, or which is applied by this gap sentence generation technique. This was inspired by the masked language modeling, yes, but more substantial, more suited towards the summarization task. So they also experimented masked language models and gap sentence generation during pre-training, and they decided that GSG is the thing to be applied out here. And MLMs and the masked language models are not improving performance for them. But in that sense, actually, how do we choose those gap sentences? So we said that the model is pre-trained with the objective of the gap sentence generation. There are multiple strategies for selecting the M gap sentences. First one, being random, is uniformly selecting M sentences at random. So whatever sentences that they have, and concatenating them together and making them as a pseudo summary, more or less. The next approach was lead, to select the first M sentences. And if you take a domain like news articles, for instance, the first M sentences could be the TLDR, could be the introduction that they use to catch the reader upon, could be whatsoever, right? This would make sense to be the most important aspect of the article. And in that case, the first M sentences would be used. And then the third one, which is the principal, would select the top M scored sentences according to the importances. So how would they model the importances? They said that the sentences are scored independently. So the sentence is scored as the Rouge score between the sentence and the document, in that perspective, for each sentence. And then the sentences with the highest score would actually be the ones that are used as top M sentences. And in that perspective, they actually covered 3 different strategies for the selecting M-gap sentences. And actually, one perspective of also, they mentioned that the one advantage of using this self-supervised objective is that we can construct those as many examples of summaries without the need for human intervention. So in that perspective, we can pre-train the model on a semi-summarization task without really that much of intervention from a human in that perspective. So the interesting part was that the model was, when it was fine-tuned on multiple data sets, this gap sentence generation pre-training allowed the model to show good performance with way less examples for fine-tuning. So if you which means that the pre-trained objective is very relevant towards the fine-tuning aspect. So if you pre-train on the gap sentence generation, then on your downstream task, if it's more or less a close-by task, which is the summarization task, then you're going to reach a good performance with way less examples, and you're going to reach your aim faster. And then they also from here concluded that with only 1,000 fine-tuning examples, they were able to perform a better task or a better job in most tasks, rather than the transformer encoder-decoder that used the full supervised data. Good results. So the PEGASUS large improved over BART in terms of Rouge 1, in terms of Rouge 2, and in terms of Rouge L. And yeah, let's actually check what do we have next. Next is the T5 and ProphetNet. So T5, they actually, I know you have touched that or tackled that a little bit also in the machine translation lecture, which makes sense because the guys for T5 said like, why not modeling any text-to-text approach as within this model? So it's actually, they say that actually it stems out from combining the best ideas together. And also maybe the title of the paper would give you an intuition about that. So the paper's title is Exploring the Limits of Transfer Learning with a Unified Text-to-Text Transformer. So they want to try transfer learning for multiple tasks being done by the same model. So as we said, the basic idea is to treat every text processing problem as a text-to-text problem. It's pre-trained on the colossal clean-crawled corpus, C4. And they said that same model, loss function, and hyperparameters across multiple tasks. This actually, one thing they did is that they added a task-specific prefix. So see here, translate English to German. So the model knows that this is a translation problem. And then here you will see summarize, state authorities, blah, blah, blah. So the model knows this is a summarization problem. And so from that, they found out that those task-specific prefix leads to soft clusters of weights. And those soft clusters of weights are actually relevant for each and every task. And in that perspective, they were able, through the same model, to perform different tasks and different approaches, different problems, different text-to-text problems in that art. So how about the pre-training? For the pre-training, 15% of the tokens are randomly sampled or dropped out. And the consecutive span of dropped out tokens are replaced by a single sentinel, which with a unique ID actually to this sequence. So X and Y here are unique. And then there is a final token that is added to the sequence, and the model is trained with the maximum likelihood to actually produce the target sequence, which is in that perspective for inviting. And last, about pre-training, let's view the downstream tasks. So for the downstream tasks, or for the fine-tuning perspective, or for the transfer learning perspective, they actually mentioned all of the tasks are casted into a text-to-text format. And then tasks where the model is fed with some text for context or conditioning and is asked to produce some output text, which is mainly like translate English to German, that is good, das ist gut, and then summarize, blah, 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 and then the summary goes out. And then to specify which task the model should perform, a task-specific text prefix is added to the original input sequence. And then the model is fine-tuned for the given different downstream tasks, which with adding this prefix is very important, using multiple data sets, mainly superglue. Then let's actually view our last model for today. And our last model for today, the ProphetNet, they had a lot of advancements in that perspective, multiple advancements, like basically an extra self-attention predicting schemes. And the other perspective is the n-step ahead prediction, which was very relevant for me to also put it on the slides for today, so that a normal this perspective is that the probability of t given y less than t and x is transferred to t plus n minus 1. So in that perspective, you are optimizing by using n-step ahead prediction that predicts the next n tokens simultaneously based on the previous context tokens at each and every time step. what they actually assumed that, or what they actually proved that this would help against, they actually mentioned that this overcomes overfitting in the summarization scheme. Now let's take a look at our final results with respect to T5. So T5 performed a little bit less than PEGASUS Large, also BART, but is actually understandable, right? Is like a model is doing 5-6 different tasks. So the other ones you probably would imagine why are they performing better. However, the ProphetNet actually is our winner for the day. So it performed as 44.2, 21.17 Rouge 2, and 41.3 Rouge L. By that, I hope that you got a good impression of what are the different approaches, or how, in a story manner, how did we start from sequence to sequence, from encoder to decoder, adding attention, going through the shortcomings of RNNs, going to the pointer generator networks. Why should we add coverage? BART, and the idea of BERT and GPT. PEGASUS, and the perspective of the pre-training aspect. T5 and the multitasks, ProphetNet, and the n-step ahead predictions. And you have good perspective, or a good view about what's happening in the research currently. And I hope by that my aim was to make you more capable towards reading and exploring and checking the tiny bits of details of each and every paper, which you probably saw the core we covered today, and is something that is changing over each and every approach, at least for the time being. So a minimal approach would be working with the slides. A standard approach would be minimal approach working with the slides plus skimming reference. And an in-depth approach, for your own interest too as well, would be skimming references, working with the slides, and reading references. I actually think the T5 paper is really interesting, so that it covers multiple aspects in our domain, in the NLP domain. Also, the rest are equally interesting. You will find all the references in the end of the lecture today. By that, thank you very much for your time, and see you next lecture.